In this lesson we'll be discussing hydrostatic pressure variation in a fluid. When we say hydrostatic, one of the key parts of that is static, so we're talking about fluid that is not in motion, is completely static. So to explain this, we're going to start by looking at a differential fluid element. So what we're saying is, imagine that we take a very, very small cube of the water. So think about water sitting in a bucket. We're just going to take one cube out of that large bucket of water. And we're going to define our axis there with the x going up, the y going to the back, and the z going up, the y going to the back, and the x will go off to the right. So this cube, this differential cube, has a length of differential x, has a depth of differential y, and a height of differential z. Okay, so it's a differential fluid, so it's just small, discrete elements. And it's going to have a mass of differential mass to go with all its differentials there. We're going to have a set pressure at wherever depth we go. And to analyze this hydrostatic pressure variation, we're going to look at each of the different axes and look at the forces going there. And just like you would do in MC300, we're going to break it down to make sure it's hydrostatic, it's not moving. The sum of the forces should equal 0. So let's look in the x direction. So we'll look at in the direction of the x, we have these two planes of our cube, and these are near the origin. You have the dimensions of dz, dy. Actually, they're both the same dimensions, both same surface area. But we start over the origin. We have the ones next to the arrows, next to that p, and then we're going to go differential distance of dx, and we'll have another plane formed by dy, dz. So we have pressure coming from both sides. From the left, it's coming, because we're doing the forces, and pressure is a force over area. If we multiply the area that pressure is going against, we can get the force. So the area is dy, dz. So we multiply the pressure by that area to get a force. And then using the Taylor series expansion, which we explain in another video, we get that the pressure, the distance differential x away from the origin, is going to be pressure going back in direction of the cube plus that change in pressure with respect to x times that differential x. Okay, so again, this is some math we got from the Taylor series. One other key element we have is pressure is always coming in. When we think about pressure acting on a body, pressure acts inward onto the body, and it acts onto the surface. So think about the pressure of the air around you. That pressure is pushing on your front, but behind you it's not pushing the same direction, it's also pushing into your back, so it's normal to its surface at all times. Okay, so we're also going to multiply that by its area, which in this case is also dy dz. So if we say the sum of the forces is equal to 0, got pressure on the left, sum it with the pressure in the other direction. We have to put a negative there because it's going in the opposite direction in terms of our how we just defined our origin. We can pull out a term of pressure times dy dz, and we see that that cancels with the other pressure dy dz. So what we're left with is that change in pressure with respect to x times the area of that cube is equal to 0. Well, we know, the volume of the cube. We know the volume isn't 0. It's a discrete volume. It's small, but it has some volume, so it can't be 0. So that means the term that has to be 0 is that the change of pressure with respect to x has to be 0. Well, if it's not changing with respect to x, then we can also say that pressure is not a function of x. So p is not equal to function of x. It's not a function of x. So what that basically means then is, as you move this fluid in the x direction, it's not going to change the pressure that it experiences. So another way to think of that is, if you're in a pool and I just go one way along the surface of the pool, it's not changing the pressure I feel of the water on me in the pool. So now we're going to look at the y direction of forces. It's very similar to the x direction. So we'll look at just the planes normal to the y direction. They're formed by dx dz planes. So we get the pressure coming in the direction of y. One side pressure times the differential area, which in this case is dx dz, and the pressure from the opposite end coming back in. Again, explaining how we came up with that pressure, you can look at the Taylor series video. It's also multiplied by differential area. So again, if we sum the forces in the y direction now, it looks very similar to the x version. We pull out the pressure times dx dz. Those pressure terms cancel, and we're left with the change in pressure with respect to y times the discrete volume is equal to 0. Well, again, we know the volume is not equal to 0, therefore the change in pressure with respect to y is 0. So we can also say that pressure is not a function of y. Alright, so now we're getting to z. So we look in the z direction, isolate those planes. We get the pressure coming below, we get the pressure coming from above. But what's new about this situation is that we also have the weight of that fluid. So that weight is also a force. It's defined as the density times the gravity times that differential volume. So density times our volume will give us a mass, and mass times gravity is our weight. So this is our weight term of our differential fluid. So now when we sum the forces, we get those pressure terms. We also have this new weight term at the end. Pull out that pressure dx dy, that cancels out. But look, now the third term doesn't equal 0. Now we get is the change of pressure with respect to z times that differential volume is equal to a negative density times gravity times that differential volume. So we can get rid of the differential volumes because they're on both sides, and we just get that the change in pressure with respect to z is equal to a negative density times gravity. So we've seen here that pressure is a function of z. So as you go up and down in elevation, your pressure will change. So from previous, we've said that if you have a differential, a partial derivative, and you say that it's now defined that it's only dependent on one variable, and we've said right now it only depends on z, we can now change that to an ordinary derivative. If we separate the variables and then integrate, we get the integral from 1 to 2, the differential pressure is equal to integral from 1 to 2 of negative density times gravity times z. Now don't get too freaked out by these integrals because we're going to take care of them in a second. So the left side just simplifies down because it's basically the integral of 1, so it simplifies down to pressure 2 minus pressure 1. On the right side, we have a negative integral 1 to 2 density times gravity times dz. Now density can change with respect to the elevation if we have a compressible fluid. Gravity is going to be constant in this case. It does technically change with elevation, but it's a very small change. So we don't really count that as a change. So we can say that for an incompressible fluid, if we can say that density is constant, and we normally assume gravity is constant as well, then we can pull them out of the integral, and it becomes a very simple integral now. And so we get that the change in pressure is equal to negative density times gravity times the change in elevation. Okay. We move the first pressure term to the right side, and we get P2 equals P1 minus density times gravity times that elevation 2 minus elevation 1. This is equation 2.13 in your book. Okay, so before we can use this equation, I want to make sure we realize there's some assumptions we make to use this equation. So the first is we called it a hydrostatic pressure variation of fluid. It's hydrostatic. So static means it's not moving. So we can only use this equation if we're looking at fluid that is not in motion. It has to be static. The other assumption we make is that we're looking at incompressible fluid. So we've talked about fluids can be gases and liquids. A gas is not incompressible. We can compress a gas very easily, so that's not a good one to use. But in most cases, we can make the assumption that a liquid is going to be incompressible. So if we're dealing with things like water or an oil, we can generally say that we can make the assumption, we have to state the assumption, but if we make the assumption that it's incompressible, then the density is constant, and we can use this equation 2.13. So those are the two assumptions you're going to need for this, that it's static, and that we assume that the fluid is incompressible. Alright, quick summary. Pressure, we talked about how it changes with elevation. You notice there was a negative in front, so pressure will decrease as you go higher in elevation, and it increases with depth. So this makes sense. As we go higher up in an airplane, the pressure will drop. If you think about when you swim in a swimming pool, if you go swim to the bottom, you start to feel that pressure on your ears. So as you go deeper, you're going to feel more pressure. As you come up from that depth, the pressure releases. Okay. So let's use our swimmer here to reiterate what we talked about. So if that swimmer there goes sideways, he goes in either the X or the Y direction, we get no change in pressure, right? So along that constant elevation, there's no change in pressure for a hydrostatic system. But if that swimmer to drop down, because his depth has increased, he's gone further down, that pressure will increase, and he'll feel that pressure on his ears.